So welcome to the 3D Deep Dive in Fusion 360. Today we're going to talk about the tool library, and in the last update we also got a little cloud library action, so we're going to talk about that. We'll go through 3D Adaptive. Containing 3D finishing strategies will actually be the first thing, and then sort of about them, like when and how to use them. This will include contour selection and then some general 3D best practices. A little bit about me. I started out before the street team, which I'm now on. I started out as a technical product manager. I'm based out of San Francisco, so I get to go play around at the pier, which is awesome. And I started out doing manual machining on Bridgeport 3-axis mills and standard 2-axis lathes, and then got into CNC and programming using SolidWorks and Mastercam, and then using HSM Works and Inventor HSM, and now using Fusion 360. And one thing that I love about Fusion, which we'll see a couple times today, is derived operations. It's cool. So with that, we will go into Fusion. So we'll start kind of from the beginning here. This is what you'll probably see the first time, maybe not this specific setup, but when you open a design in Fusion, you're going to probably be in the modeling workspace. And that's all well and good, but as we can see, every command in my toolbar up at the top here is a modeling command, so I don't see any CAM stuff yet. But to get to CAM, I'm going to go all the way to the left. In the workspace dropdown, this is how I can change workspaces. So if I want to get to another workspace, I'm going to come over here, go to that workspace, and just click. So to get to CAM, I'm just going to go select a CAM, and now I'm in the CAM workspace. Didn't have to export a file, didn't have to do anything crazy. The UI looks almost exactly the same, and I can tell I'm in CAM because all my commands are now CAM related. So making a setup, different types of operations, the actions of post-processing and things like that. So before we actually jump into using the tool paths, we're going to talk a little bit about tool library, because I think personally this is the very first thing you should do when you are getting set up with Fusion. So the tool library is here to represent the tools that we have in real life. So to get to it, I'm going to click on this folder with a tool under Manage, and this window pops up that I like to call the Tool Library Manager. This is where I can go into my libraries, edit my tools, organize my tools, create new libraries, delete libraries, all that kind of stuff. So the main portions are in the middle. We have a list of all the tools. So if I click on them, a little model shows up over here on the right, and I can scroll through and see all the tools in the selected libraries. And on the left, we have something called the library tree. If you don't see this, it's probably hidden, so there's a toggle button in the upper left-hand corner to show and hide the library tree. I would make sure that you can see it. And then we have 5 different types of libraries. A document library is wrapped up in a Fusion design, so you can see the titles here, containing 3D Toolpaths, version 9. This corresponds to this design that I have open. And the other one, 3D Toolpath Examples version 5, corresponds to this design that I have open. So these are tools that I've used to program inside of a design, and then when I hit save and create a version of that design, Fusion just wraps up those tools inside that design as well. So if I were to send these to you, you'd be able to see all these tools. The next kind of library is a cloud library. These are tied to my Fusion account, so anywhere that I sign in or log into Fusion 360, I'm going to be able to see these. And you do have to enable cloud libraries and preferences to see this, which we'll go through at the end of this tool library section. But basically, these are tied to my account, so I'll see them no matter where I log into Fusion, and I can edit and create them just normally. So when I'm in the cloud section, I can add a new library. There's a new cloud library now. I can, add tools and things like that. And I'll go through that at the very end when we get to local. The next type of library is a sample library. So these are all just like generic sample tools. Like every size of drill you could think of, pretty much every fractional size of end mill, I think going up by like the 16th of an inch, a radius mill, like just generic tools. And there's no option to delete these libraries or edit them at all. You can't edit the tools. You can only copy them. And this is because we sort of looked at this as like a way to make sure that everybody has a tool that they can play around with and, you know, actually go in and get their hands dirty programming, but we didn't intend for them to be used like for real. The preferred workflow is for you to create the tools that you actually have and then use those ones. So they are just samples, but they are here to be used. I typically turn them off, and by turn them off, I mean these checkboxes indicate visibility. So if I uncheck the top level, it unchecks all of them, so I won't see any. Or I can uncheck the top level and then say, well, I do want to see inch titanium tools. And now when I am choosing a tool to use later on when I'm making an operation, only that sample library will be visible. So that's kind of what the checkbox means. Then we have vendor libraries, and these are similar in that there's no way to edit these. They're always there. They will always be in Fusion. I can't edit any of the tools, can't edit any of the libraries. However, they're based off of like actual vendor catalogs. So they are intended to be used, and they're intended to you know, instead of you having to create every single tool from scratch, if you have one of these Mary tool holders or one of these Tormach tools, you can just come in and select this instead and use it. So the plan is for this to continue to expand and get bigger so that we can support more and more vendors and more users with these vendor libraries. And then last, we have local libraries. These are stored on the computer, like on the physical laptop rather than tied to my Fusion account. So anybody who logs into Fusion on my laptop is able to see these libraries. They exist locally on my hard drive. And this is where I'm going to spend most of the time talking about like actual library commands, but everything I do here in local also applies to cloud. They function the same, just one is tied to my account, one is tied to my computer. So the first thing we're going to look at is library commands, and if I am in here, I have 5 commands that are all kind of grouped together. These are library commands. The first one is to import a library. So if I am coming from Inventor HSM or HSM Works, those library file formats are all the same. So I can save out that tool library and just import it into Fusion really quickly and easily. Similarly, we have export, so I can generate a library file from this file, save it out somewhere else, and like maybe send it to somebody else, send it to HSM Works, my friend who uses HSM Works who has the same tools as me, or save it on my laptop somewhere. So it is recommended that if you choose to use local libraries, it's kind of a good best practice to export them and save them outside of the Fusion directory. So if I hit this button, it takes me this path up here is inside of the Fusion directory files, but if I save it just like anywhere else, if there is an issue with Fusion overwriting the libraries, it won't affect it. So it's just a nice like backup, like backing up your laptop basically. We also have duplicate, so I can just make a copy. This can be really useful if you want to set up several libraries for different materials until, so like rather than changing feeds and speeds every time, just setting up a whole one for your mill, that's for steel, a whole one for aluminum, things like that. And then I can create a new library. So this just makes a new completely blank one, and then I can enter a new library name. And then I can, of course, delete a library. So once I have a library, especially if it's an empty one, I need to start filling it with tools and holders. So to do that, over here we have our tool commands. The first 3 are all creating a new one, so new mill tool, new mill holder, new turning tool, and then we have some like editing commands, like edit a tool, renumber the tools, or delete the tool. So we'll start by making a new holder. Under general, pretty much all of this like general information is just for you to know like about your tool holder later. We don't really need it on the Fusion end for anything, but like if something, if this holder breaks or I crash it into the table or something, now I just know all this information without having to go like scrounge up the, order sheet or whatever. And to create the holder, I'm going to add sections of geometry one by one. So I would recommend like having the manufacturer drawing nearby, and this process is a little, it's different when you first start doing it, but basically you're going to put in sections of geometry one at a time. They go from the top to bottom here corresponds to the top to bottom here. So you want to start at the top of your holder, the part that would be going in the spindle, and then you just sort of add geometry. And keep adding geometry, and keep going until you get to what your holder looks like. And then, so I would keep doing that if I was like to actually create this holder in real life. And then if I need to delete a section, so if I realize this is wrong, I can select anywhere in the row that I'd like to delete, and then hit the delete key. I can also change units in this upper corner. So that's how I would go about creating a holder. I'm going to just not use this one, but that's the process. And then to make a new mill tool, we click the new mill tool button, and it's similar but a little different. For tools, there's a lot more guidance, and you do need to actually pick from a list, from a pre-populated list of types. So there's no form tool or like uploading your own sketch or model or DXF or whatever. You do have to actually make it from one of the types that already exist. You can create a lot of tools that aren't listed here, though, by just kind of, putting in geometry that you wouldn't expect to see in that kind of tool. Yeah. So put in a little bit about it. What's the material, temperature coolant, unit. You can have metric or inch tools. Do note that if you pick metric here, other tabs like feeds and speeds will also be in metric. Just something to note. Putting in the number of flutes is important. It'll use that, Fusion will use that later down the line for a bunch of calculations, so make sure that's accurate. And then just like before, this description is just for you to know. The description will be put next to the tool though, so if you have a bunch of different bullnose end mills that are the same diameter and the same approximate length, it might be good to just denote what makes them special. And then over here on the right-hand side, we have parameters about the tool. So like the diameter, the corner radius, the shaft diameter. If I put in a different shaft diameter right now, it's just going to have a really sharp shoulder. In the next tab, the shaft tab, I'm going to be able to control that a little more accurately. So I'm just going to leave it the same for now. In the lengths section, Fusion always highlights from the bottom of the tool to the top of the selected length. So for the flute length, it's going from the tip of the tool to the top of the flute. And then in the next one, the shoulder, it's going from the tip of the tool to the top of the shoulder. So I know it's a little confusing, but basically heights or lengths are cumulative. You're going to keep adding. Body length highlights the whole thing. And what that is trying to tell you is this is also the stick out length. So this is the total length that's coming out of the holder, basically. And then overall length, when it highlights nothing, this means if you were to take the tool completely out of the holder and measure it from end to end, how long is the tool? So between these two values, you can actually figure out how much you're holding on to as well, which can be good to know. So in the shaft tab, this looks exactly like the holder geometry tab, and that's exactly how it functions. So it's the same exact type of thing. You can put in the height, the upper diameter, and the lower diameter. And then just like before, when I add more sections, it still goes from top to bottom. Oops. So this top part corresponds to this upper tapered section, and this bottom one corresponds to this lower tapered section. So This is how I can add shaft geometry that's not just a sharp shoulder, but if there's a taper or something like that. And then same thing to delete, I'll just hit the delete key. Under holder, I can select a holder. So this is where like creating your holders first is a good idea, just because then you can assign the tool to the holder or the holder to the tool right away instead of having to go back, create your holders, and then assign them to tools. So I can pick a tool from any or a holder from any library when I'm doing this. So I actually get like all my enabled library holders show up. So I can pick a Tormach holder. I could pick one of these Mary Tool holders. I could pick one of the Uber trucks. Whoa. And then when I choose a holder, now when I go back to like that preview of the cutter, it's going to show me those two added together. So I see now that the body length is the part that's like actually physically sticking out of the holder. In the feeds and speeds tab, I can assign feeds and speeds to this tool, and these will be kind of like the default feeds and speeds. So when I select this tool for an operation, these are going to be imported into that operation, but I can always change them for that individual operation. So I like to think of these as like 90% of the time or 60% of the time, what are my go-tos for this particular type and size of tool. And obviously it's not going to be the same every time, but just kind of a standard feeds and speeds. So for example, like our Haas mill goes to 12,000 RPM, and I usually am cutting aluminum, which like 3/1000 of an inch is probably fine. So maybe this is a good starting place. Maybe if I'm like really roughing stuff out, I want to go to like 4 or 5. Maybe this is my good starting place. So it depends on the tool. And as you guys noticed that I just did, you can obviously either enter a direct spindle speed rate and cutting feed rate. So I could just put in, 150, or I can enter the surface speed and feed per tooth values. So these are both calculated using tool parameters like diameter and number of flutes, which is why it's important that those are correct. Otherwise, all these values will be wonky, but I can totally go, backward like the other way as well. Cool. And then and then down here I have my vertical feeds, so plunge feed rate and the feed per revolution for plunging. So like that's probably more appropriate. And then under post processor, this is where I'm going to set the tool number and the offset values. So typically these need to match, which is why if I change the first one, the other two will update with it. I can also set the turret that it's in, since we now support multiple turrets, and then I can add a comment to be posted when the tool is posted. So when I hit OK, I'm saving that tool. It's now in my library. When I click on it, I get a preview over here. And I would repeat that process for all the tools in my library. One thing that I can do is, like, if I had another half-inch bullnose that was really similar, but maybe it was for roughing, or it was for aluminum only, or had 2 flutes or whatever, I can also just right-click and select duplicate, and then go in and make any edits. So like maybe I'll increase the tool number by 1, and then I'll say 2 flutes, plastic only. And then obviously I would need to update the feeds and speeds, but it's a quick way to make tools without sitting there and putting in the same parameters over and over. Another quick trick is if I just duplicate these tools a whole bunch of times, which is, I'm going to pretend is me making a bunch of unique tools, but they all have the same number. So one quick way to renumber all my tools is to use the renumber tools command. So I'll pick all of them, come up to renumber tools, and then I can enter an initial value, we'll say 1, and then an increment value. So let's say we go up by 10. I want to make sure all these boxes are checked to update the length and diameter offset values. And then when I hit OK, now they're renumbered 1, 11, 21, 31, 41, 51. So starting at 1, going up by 10. Yeah, I think that's that's about it on this portion. So the thing that has changed now is that cloud libraries, while they appear here, they also appear in my data panel as a new project called assets. So at the very top project level, I see all my projects, and then there's something called assets. And this is where cloud libraries, posts, and templates now appear. So if I click on CAM Tools, this is where both of those cloud libraries that I saw in my Tool Library Manager now exist here. So the Haas Mill is this one, and the Pier 9, oh, they're the same, but they're both here as well. So I can get tool libraries into Fusion also by uploading them to this folder rather than importing them in the tool library. And then the same goes for templates and posts, which we'll get to later. But just so you guys know, this exists now. It's another way to access your data and effectively be able to use and share it. Okay. So tool libraries. Jeff asked, is there a way to turn them off and make mine the only one? I'm pretty sure the answer to your question is you would just uncheck. You can't uncheck document libraries. They're always going to be there, but you can uncheck vendors, uncheck, all the samples. You can't delete any of these. Samples and vendors will always be there. Cloud libraries will always be there, but you can effectively turn off the visibility of all the libraries that aren't yours. Or if I was doing a lot of lathe work and I wanted to only see my local lathe library, I could just uncheck everything else. And then when I close this tree, that's the only one that's going to appear. Even when I go to all. It's just the document libraries and the lathe library. So that's the answer. You can't get rid of all the other ones, but you can, uncheck the libraries that aren't relevant to you. And then, because I said we would, we'll look at, if you click on your name in the upper right-hand corner, you go to Preferences. Under General CAM, this is how you enable cloud libraries. Just check this box. And then I think right away they should show up. You should have a new cloud libraries folder in your library. Okay. So now we're going to get into it. So the first thing, we're going to talk about setups pretty quickly. There is some stuff in the 2D deep dive that I go through a little more thoroughly than in 3D. There's just a lot to talk about with 3D, but one of those things is setups and kind of the whole setup process. So in order to make any kind of operations in Fusion, you need a setup. To do that, all the way to the left, there's a icon that looks like a folder with a cube inside called Setup, and when I pick this, it takes me to the Setup dialog box. So it did a thing where it grabbed all the models in my workspace and put a big yellow box around them. That box is a preview of what it thinks I want my stock to be, because it's assuming I want to machine everything that's in my workspace, which isn't exactly correct. So we'll come over here. The first thing we want to do is make sure that our operation type is set to the correct thing. So we have milling, turning your mill turn, and then water laser plasma, which is a preview right now. So if you're not seeing this, that's okay. I've enabled it as a preview. So we're going to stick with milling. Then under model, we can come down here and see that it selected all 68 bodies that were in my workspace as the thing I want to cut, or the actual part. This is not correct. So I'm just going to clear them all out and pick the one part that I actually do want to make. And now it'll update, it's updated that stock preview to something that's way more reasonable. It's only snapped around this one body. Next, I'm going to set my work coordinate system. So here I can do the model orientation. So if I designed everything with my machine or manufacturing in mind, maybe I can just use all the default model stuff. But if not, if it came from a designer, or if, just wasn't being thought about, I can also define based off of the actual geometry. So I can pick any two axes to define the whole work coordinate system. I usually do Z and X, but sometimes X and Y is better. So I can choose any two, and I'll do Z and X. And when I'm selecting these axes, I can pick any face that's perpendicular or edge that's collinear with the axis that I, is that right? Any edge that points in the same direction. So for the Z, I can choose this top flat face. And for X, I could choose either a pointy edge like this, or I could choose another face and it'll be perpendicular to that face. So either a face or an edge works. If I needed to flip any of these axes, I could do it in one of two ways. I can either click on the tip of the arrow, or I can check the box in the dialog box. Either way works. Then to define the origin, I can choose from the model origin. So again, if I designed with the origin already in the right spot, awesome. I can also use a stock or model box point, and these box points are at the midpoint and endpoint of any vertice or face, where they're at the vertices of the box and then also the midpoints. So for a stock box, for example, if I chose this outermost point, this is something I could probe in the machine on my actual stock. So I just probe this outside corner, and that's how I would define that origin. Last but not least, I can define my fixturing, so I can choose bodies that are fixtures. And basically what this enables Fusion to do is during a stock simulation, if there's a collision between the tool and the fixture rather than the tool and the stock or something like that, it'll be able to tell me, hey, your tool hit your fixture, rather than just saying there was a collision, but I don't know what it was. In the next tab, we can define our stock. So this is where I'm going to tell Fusion the dimensions of the actual stock. So I can choose from a fixed size or relative size box, cylinder, or tube. So those are pretty straightforward. Fixed meaning I'm going to put in the actual dimensions. Relative meaning I'll put in an offset value and it'll offset from the part model. And then at the bottom, there's something called from solid, which basically means that I can choose a body that's been modeled and make that the stock. So this is really good for like second setups or something where I've already removed a bunch of material. It's also really good for if I, put my part on the water jet and cut out the outer contour first, then I can have an extruded, a big extrusion of that shape rather than just having like a big square and wasting a bunch of time cutting material that's not really there. So I'm going to do a relative size box, and I'm just basically going to get rid of the side offset. And at the bottom here, I can see the dimensions of my stock. So it's about 1.5 inches by 1.5 inches by 0.915. If I did a fixed size box, I could actually put in dimensions myself, and it usually rounds up to the nearest 1/2 inch, but this is there for like, standard stock sizes. Like usually your stock is going to come with 1/4 inch being like the smallest deviation. Last but not least, under post-process, I have the option to add a program name or comment right now. I usually wait and do this at the end, so I'm not going to touch that yet. I have like 2 or 3 more opportunities to do that in the process. But what I do need to do is make sure that if I'm doing multiple work coordinate system offsets that are unique, I need to make sure that this starts at 1. Oops. Because 0 points to G54, but 1 also points to G54. So 0 and 1 are both the first offset. Then 2 would be like G55, 3 would be G56, and so on and so forth. So I just need to make sure that I'm starting at 1. And then last but not least, this checkbox down here, multiple work coordinate system offsets, is actually just a copy of this exact setup. Like all the operations that go in the setup, it would copy them however many times you say you want to. So if I say like, I want to make this exact part 4 times, in the post, it's going to post this exact same set of operations 4 times with 4 different offsets. So then all I would have to do on my machine to do that is just probe 4 different locations, and then it would run the same part at those 4 different locations. Hopefully that makes sense. But it's just a quick way to like do the same thing a bunch of times without having to make literal copies of that setup. So that's what multiple work coordinate system offsets does. I'm going to uncheck that for now. I just want one of these, and then I'll hit OK, and now I have a setup. I can rename this setup something more descriptive, like I've renamed all these setups about what's inside of them. That's not a very good name, but it's okay. And it's the active setup. So it's got this little radio button next to it is enabled. If this were the active setup, any new, even if this one is the one that's selected, any new operations that I make are automatically going to go into the active setup folder. So if I were to make 2D adaptive right now, it's going to show up here, even though I just made this one. So you want to make sure that the setup that you want your operation to go into is the active setup. Okay, so went over setups, and now we're going to talk a little bit about 3D adaptive clearing. So to talk about it, let's just make one. 3D adaptive clearing appears under the 3D dropdown. It's the very first choice, and it should be in everybody's toolbar. So 3D adaptive works based off, actually, just kidding. We're going to talk about facing really quick because we're going to take a look at how operations in Fusion are programmed. So the first thing that we're going to notice is that in my operation dialog box over here, there are 5 tabs, and this is the same, or this is true for every operation in Fusion, where the first tab is the tool tab. This is where I'm going to choose my tool, and this is where I have the option to edit feeds and speeds for this particular operation. In geometry, I'm going to tell Fusion and this operation which areas of the part I want my toolpath to be applied to. In heights, I'm going to be able to set a top and bottom height for the operation and then define the clearance and retract heights as well. Under passes, I'm going to be able to tell the tool how to cut the material. So this is where I'll find things like step down, step over, direction. And this is the tab that tends to vary the most from operation to operation. And then last we have linking, which is going to define how the tool moves between cutting passes. So how is it linking those cutting passes together? So let's apply these 5 tabs, and pretty much all programming in Fusion is just applying these 5 tabs and the principles of those tabs to the operation. So the first thing is we want to pick an appropriate tool. So facing operation, probably not going to use a ball end mill. I'll go into my tool library and pick something more appropriate. So let's say I want to pick a face mill. I have these filters on at the top. I can use them, so I could say, well, I don't want a ball end mill, don't really want a bull nose. Let's filter out to only flat and face mills and see what we get. So nothing in my document library is flat, so I'll pull up this face mill from my Haas mill library and hit OK. If you really don't like these filters at all, there's also an X in the upper right-hand corner to just clear all the filters. And now I'll see every single tool that I have available. I can also edit my feeds and speeds, and any changes that I make here are just for this one operation. They won't save back to the tool library. They're just only going to apply to the specific operation that you change them for. Next, under geometry, I want it to go across the whole part, so I'm not going to make any selections here. I'm just going to let it go. And under heights, it defaults to the top height being the stock top and the bottom height being the model top. So it's just going to lop off that little hat of stock that's on top of the part, which is exactly what I want. and I'm good with all the other defaults, so I'm just going to hit OK. And now I get to see a preview of my part and toolpath. So here's a model of the tool, which is generated based on the parameters I put in when creating that tool. And then this is a preview of the toolpath. So it's got yellow for a retract move, so it's going to come down. Green is a lead-in. Blue is cutting. And then we have a green lead-out and a yellow retract. So I can kind of see what the tool is going to do just based on this preview without having to run any kind of a simulation or anything like that. And the arrows at the end of the toolpath lines indicate the direction. So I can see that it's going to start over here and finish over here. So now I've kind of just like gotten rid of the stock on the very top of the part, and now it's time to clear out these pockets and the rest of the remaining stock. So now I'm going to do a 3D adaptive, and in the Tool tab, I obviously do not want a 2-inch face mill to do a roughing operation, so I'm going to go in and pick this 1/4-inch bullnose. And when I hit OK, it updated all my feeds and speeds to be things, to be what was put in for this tool library, for the tool library for this tool. So I can make any edits that I want right now, and set those feeds and speeds for just this operation. In the geometry tab, I want it to apply to the whole part, so I'm not going to pick any geometry. I'm going to let 3D Adaptive calculate over the whole part, which is what it's going to do. So 3D Adaptive is going to actually look at the geometry itself and find where it can remove stock and go in and remove it. So under heights, I want to make sure that it's going all the way from the model top to the model bottom, able to remove all the material. And under passes, here's where, for adaptive clearing specifically, I can set things like the optimal load. So the way the adaptive algorithm works is it goes in and calculates the toolpath based on a constant engagement angle. So it's always going to be engaging the same at the same angle on the tool. And then the optimal load is when it's become fully engaged, how much of the tool is engaged at once. So it's similar to a step over, but not exactly the same. So 0.1 inches seems like an awfully arbitrary value. And where did this come from? Who knows? If I right-click in this text input box, I get a bunch of options, and one of them is Edit Expression. So here I can see that this is actually a formula, and it's the tool diameter times 40%. So now 0.1 seems a little less arbitrary. There's actual math behind it. If 40% seems like a lot, I can, of course, turn this down. So I could say 25%. Or I could turn it up and say 70%, depending on what I'm cutting, how I feel about my tools and my setup and things like that. So you guys are definitely welcome to, go in, edit, make it something that you're comfortable with or more or less aggressive. I'm going to put this at 30% just for fun, and when I hit OK, it's going to update that value to be the result of this formula. So now it's 75 thousandths. If you come up with something that you love and you always want it to be that percentage, so like 32% or whatever, you can say make default, and if you select make default, for every new 3D adaptive clearing that you make, the optimal load will always be whatever I said, 32% of the tool diameter, or in this case, it'll be tool diameter times 30%. Or, yeah, 25%? I don't remember what I made it. Okay. Also in here is the maximum roughing step down. So the way that 3D Adaptive works is it basically takes one big step down at the maximum step down level, and then it does a bunch of fine step ups. So it takes the biggest cut first and then goes back and does lighter and lighter cuts until it's done. So this is like the deepest cut that it will make, and it's by default I think it's 10 millimeters. I'm comfortable going a little deeper than that, so we'll say maybe like 0.5 inches. And then the fine step down, those little step ups that I was talking about, always default to 1/10 of the maximum roughing step down. And then the last thing in the passes tab is the stock to leave values. So we have radial and axial stock to leave, where radial is sideways, like in and out of the tool, or left and right, and then axial is up and down. So I can either put in two separate values or two that are the same, and basically this is how much stock is going to be left behind. I'm going to keep both of them because it's a 3D part, and I would recommend, and the recommendation is that you leave stock to leave on so that you can come back and clean up your part with finish passes, because adaptive clearing is a roughing operation. And then finally, under linking, adaptive clearing I think probably has the most complicated linking tab of all the operations. Usually it's pretty straightforward, but what adaptive clearing adds is some stay down options. So the first one, the maximum stay down distance, this is like, it compares the retract move to the stay down distance move and says, oh, just kidding. This is like how long of a stay down move is acceptable until it goes back to just retracting. So on the left of this tooltip, we have it can stay down for up to 1 inch, and then on the right, it can stay down for up to 2 inches. So obviously, more stay down moves happen when this distance is longer. So for this part, these parts are pretty small, but we'll just put in 3 inches. Then maximum stay down distance, or maximum stay down clearance, is the distance it needs to maintain between the tool and any obstacles it might encounter. So the bigger the distance you put in here, the more it's going to avoid obstacles, and if it can't avoid them with that clearance, it'll just do a retract move instead. The stay down level is like how hard it's going to try to do a stay down move, or another way to think of it is like it looks at the retract move and it looks at the stay down move and it compares them, and this is kind of like the tolerance with which it will choose the stay down move over the retract move, if that makes sense. So the higher the stay down level, the more stay down moves there will be. If you choose most, it'll actually override your maximum stay down distance, and it'll just do stay down moves for as long as possible while respecting the clearance. So I usually go for like 80%-ish. Do note that if you have a really long adaptive clearing toolpath and it's really complicated and takes a lot of generation time, this will add to that generation time. So the calculation time increases a bit when you increase the stay down level. Lift height will add a vertical lift to any stay down moves. So this tooltip shows it pretty well. There's just like a little lift. And then no engagement feed rate is how fast the tool is moving during the stay down moves. So I usually go at least my cutting feed, if not more, and then typically something a little closer to rapid to like really save time in these stay down moves. And then last thing is the ramp type. So because I'm going to enter into like a closed pocket, I need to have either a pre-drill or a helical ramp. Because I didn't make a pre-drill, I'm just going to go with a helical ramp. And now I'm ready to hit OK and let this generate. So when I scroll in here, we can see kind of what I was describing, where that constant engagement angle leads to some really like the transitions into the cutting moves. The blue lines here are like really gradual and gentle, and then it gets up to that optimal load, stays at the optimal load for as long as possible, and then exits the cut. And then scrolling closer, when it enters a corner, it's still doing that same engagement angle, and it's keeping like a really nice smooth transition on the tool. So it's never going to overload in a sharp corner or anything like that. It's always going to take that nice smooth pass. And we can also see, it's a little hard to tell, but that fine step up is the fine step down is the distance between all these passes. And then if we actually simulate this, And I'm going to do that by selecting both operations, right-clicking, and choosing Simulate. We'll be able to see that it takes the biggest cut first and then does the rest. Okay, so I'm going to back up for 1 second. So I entered the simulation environment, and over here in the display tab, I want to make sure my tool is on, so I get to see my tool. Toolpath is also on. I usually like to do tail, which just follows the tool around for a little bit. And then under stock, you definitely want stock enabled because this is going to show you what your stock's going to look like as it's being machined. And then my personal preferences are ceramic for the material and operation for colorization. If we go into fast mode, there's more choices, especially for colorization, but I still prefer operation. And then if you are in fast mode for some reason, definitely make sure you're at a high or extreme level of quality. And I would recommend that if possible, you use standard mode. It's just a better quality simulation. And if you're simulating anything higher or more complex than 3-axis, you have to use standard mode. So we'll keep going. So it's now changing colors because I'm in a different operation. I can see how the tool is going to move and what the stock removal looks like. So I can also see we're taking our biggest step down first, and now we're going to go in and take all those fine step downs, so all those shallower depth of cuts. And it'll do the whole operation in that kind of stair-step way where it'll cut all the things at that one Z height and then move up and cut all the things at the next Z height, move up, move up, move up, and so on. While this is going, so we can see it kind of missed a little chunk down here, but that's because that was the lowest, that was the maximum roughing step down. The other tabs in my simulation are info, where I get a live XYZ feed. So this is pretty much what I would see on the controller. I get some information about the operation, the current operation, and then at the bottom we have something called verification, which basically is going to tell me the total number of collisions and then the start and finish volume. And then the final tab, statistics, gives stats on all the operations that were simulated. So like the total runtime, the total machining distance, things like that. Okay, cool. So if you go back to display, we can turn on transparent stock, and we can see pretty clearly that there's a lot of stock left in these pockets, that this tool was just too big to remove. So I need to add some more roughing operations, but so far this looks pretty good. We can see that kind of stair-step effect left behind by adaptive clearing, which is why we definitely need some finish passes. So we'll close this. And this time I'm going to add a 3D pocket instead, just to kind of see the differences between 3D adaptive and 3D pocket. And I'm going to pick a smaller tool, so I'll pick this 1/8 inch tool nose. Under geometry, I am actually going to add a bounding box because I don't need it. I don't need this toolpath to do anything on the outside here. I really just need it to get inside this boundary. So I'm going to add a machining boundary. My choices here are a bounding box, which is just a square that encompasses the part. A silhouette, which is the outside shape of the part, and a selection, which I'm going to pick actually off of the geometry itself. So I'll go down to selection, and I'll choose this contour. So now all the toolpath that's generated is going to be on the inside of this contour. Under heights, I don't really need to change any heights because I want it to do from top to bottom of inside that contour. And under passes, I just want to make sure stock to leave is on. So I'll hit OK. And that is a full-on pocket there. So I'm going to cut a lot of air, right? Like we know that a lot of this is already empty. And that's because I did not enable rest machining. So under geometry, there's a checkbox here for rest machining. And what this is going to enable me to do, or enable Fusion to do, is if I select from previous operations, it's going to look at what was removed in face and adaptive, and it'll know that that's already gone, so it doesn't have to cut there again. So now when I hit OK, it's going to generate something with a lot less toolpath because it's going to take into account what's already been removed. So this looks like it's going to take way less time, and it's only taking away material that was left behind by that 3D adaptive. And it's also cleaning up some of these corners because I'm using a smaller tool. Sweet. So we could run another stock simulation just to make sure. Select all the operations, right-click, hit simulate. Go ceramic, operation, hit play. And because I've already watched the first two and I know that they're fine, I can use this go to next operation button to just skip to the operation I actually want to see. So this is the 3D pocket where it's going to go in and clean everything up. This all looks pretty good so far. And because I can see that in verification I have no collisions, there's no collisions in my timeline, I could also just skip to the end of the toolpath. And now I see that those pockets are much more cleared out. And also worth just noting that this is what a typical pocket operation looks like, where there's just offset passes, versus this adaptive where we can really see the difference between the offset passes and the smooth transitions of adaptive clearing. Okay, cool. So my part is completely roughed out, and now it's time to do some finish operations. So we're going to switch gears into finishing and into containment specifically. So for this part, I'm going to want to do a finishing operation to get, this pocket all finished up. And if I look at it straight on, it looks like all these features here are running kind of like in approximately the same direction, but there are some draft faces, and draft faces are notoriously difficult. One thing I might try is a parallel operation, just for fun. Most of it looks like parallel could handle it pretty well, but we'll see how it fares on those draft faces. So I'll make a new parallel. I want to pick a ball and mill this time. Under geometry, we're just going to have it do this inside portion for right now. I don't need to pick any heights because it's just going to go top to bottom in that pocket. And then under passes, for parallel, the things that I want to make sure are nailed in are the pass direction, so which way the passes are pointing. By default, this is 0 degrees, which points 0 points along the x-axis and 90 points along the y-axis. So 0 is kind of like the opposite of the direction that I want to go. So I'm going to say 90 because everything appears to be running. We can see y is pointing this way, which is about how all the features appear to be running. Both ways is fine, and for step over, we'll say maybe 25 thousandths. Under linking, for most of these operations, the only thing I'm going to change is the retraction policy. Full retraction always goes to the clearance height. Minimum goes to a safe height determined by the safe distance I put in down here, and shortest path just goes like in basically a straight line or a bunch of short lines to the next point. So I'll choose minimum retraction and I'll hit OK. Okay, so from the top, this looks pretty good. If I look right from the top, I can't see anything. But I can see how this is like parallel is basically just a bunch of lines back and forth, right? Or like so it appears. When I look at it from the front, it still pretty much seems like a bunch of lines back and forth. But when I look at it sideways, I can see that it didn't do so well on those steep faces. So it's just a projection. It's just a bunch of lines drawn back and forth projected onto this 3D surface. So it's not really handling these steep walls very well. It looks like it handles these dips and this like little feature in the middle, and that all looks really good. But I want to make sure those steep walls get machined, of course. So there's a lot of ways to handle that. One way would be to go back into this parallel and under passes, just make a quick change to say machine steep areas and then say OK. And now Fusion went ahead and added extra stepovers for those steep walls, so that looks a lot better, right? Like those steep walls look like they're handled, but this is really going to up my machining time because of all these extra passes. The other thing I could do, if I just duplicate this to make an exact copy, I could say machine straight on and add perpendicular passes. So add perpendicular passes is going to add a set of passes at 90 degrees, and machine straight on is going to only have it, only put the parallel where it makes sense. So now I effectively have two parallels that together can machine this whole thing. But my surface finish might look kind of weird. I'm going to have a bunch of like 90-degree lines, but it's an option. So those are two ways to like, even though parallel isn't the best fit for this geometry, I would say, there are ways that I can make it work. There are changes I can make to improve how it's going to machine the part. However, I can also use a completely different strategy. So let's say I just go to this first parallel, and this is like, this isn't awful, but I want to quickly generate a different kind of operation using these same constraints. So using the same machining boundary, using the same tool, using the same whatever. I can right-click on this parallel, go down to Create Derived Operation, and now I can choose any of these other 3D operations to create using the parameters that I defined this parallel with. So basically, what I'm doing is looking at this parallel, finding all the parameters that apply to the new type of operation and porting them over. So instead of having to get one from scratch, put in all the things, I'm going to just like dump everything from this parallel into a new operation right away. So I'm going to pick a scallop, and I'm just going to hit OK. Uses the same tool, use the same machining boundary, use the same step over, all those things. It just generated a different type of strategy. So now I have a scallop. I can see that it's handling those drafted faces a lot better already. And yeah, it looks like it could be a good fit. So I just like, without looking super far into it and like running a stock simulation and everything, I can just already quickly see from the Toolpath preview a bunch of different types of strategies, basically. Okay, so now, last thing, let's say I'm happy with that scallop. Last thing I need to do is create a parallel for the outside of this little pocket channel thing. So I'm going to make another parallel. This time, under machining boundary, I'm going to actually pick two. So I'm going to pick first this inner pocket one, and now to keep it out of that machining boundary rather than keep it in, I'm going to also pick one outside of it. So when I have a machining boundary inside of another machining boundary, the toolpath is going to go between the two boundaries. And this one on the bottom, we can see, doesn't quite make it all the way out to here. So what I could do is select another one, but then I have like 3 machining boundaries selected, and I really don't actually want that. So what I'm going to do instead is do some contour editing. So I'm going to pick this first contour, and this takes me to contour editing, contour selection editing. So right now, the blue line is the one that I've already chosen, so that's the one that I originally selected, and the black lines are all the selections that Fusion automatically made. So Fusion kind of assuming what I want. So to edit this, I can just make another selection. So now that one's also blue, and the black line's updated to include that in the selection. I could also, like, if I wanted it out of this upper part, nope, okay. So now it's including the whole part, including this bottom face. I'm good with that. So I'll hit accept to save my changes. If I hit cancel, I would keep the contour selected, but not save my changes. And if I picked delete, I would just completely erase this selected contour, basically. So I'll hit accept. And now it updated to go all the way out to the edge here. And now I'm ready to move on. So I have my machining boundaries selected. Under heights, my top height is currently the stock top, but I actually just want it to go to the model top. And actually, even then, I've already faced off this part, so I could even have it go like to a selection and pick this top edge. And I don't think it'll go all the way up and over, but we'll find out. So I can choose a height based on any other height or based on a geometry selection like I just did, and then add an offset, either positive or negative, where positive is up in the Z direction and negative is down or in the negative Z direction. Under passes, I want to make sure this is 90 degrees because all my features are changing Z in the Y direction. The Z changes in the Y direction. And we'll make my step over a little smaller. And linking, I'll set to minimum retraction and hit OK. Cool, so that looks good. Parallel seems like a good fit for this. If I wanted it to stay off this top face, I could add a small negative offset here. And now it should stay off the top face. And there we go. So that was using, the point of this first part, I know I talked about this first part for a long time for roughing, but the finishing point being made was that containment or like machining boundaries are a good way to contain toolpaths. So either inside of a machining boundary or between two different machining boundaries. And I can also use heights, like to keep things off this top face. I can use heights to achieve that. Okay, so in this whole palette of parts, these three gray ones, I'm gonna use a lot of selections where I like choose directly off the geometry and affect the toolpath that way. And all the orange parts are going to be ones where an intrinsic property of the geometry, like the slope or something else, is automatically going to determine how the toolpath is generated. So just, that's what the colors are. So in the next part, we're going to look at model, and I'm going to use this setup here. So the first thing is a 3D adaptive that was just generated. It's a normal 3D adaptive. So under geometry, nothing fancy. There's no model selection. Under heights, just the basic stock top to model bottom. Under passes, standard optimal load, so basic 3D adaptive essentially. And I guess I should back up. In my setup, the thing that I chose as the model was this gray body. So that's what Fusion expects me to want to cut. So when I generate this first 3D adaptive, that's the model that this toolpath is looking at, because that's the one that I defined in the setup. In the next 3D adaptive, under geometry, I enabled model at the bottom, and rather than using the model I defined in the setup, I can override this. So I can override that setup model by selecting a different body. So in this case, I'm going to pick this blue body with the walls. And underneath, I have the option to include the setup model, which means that I would just be adding to it. So when calculating this toolpath, Fusion would respect both the setup model and the model that I'm defining now, or if I uncheck this box, I'm completely overriding the setup model. And in this case, specifically, it doesn't matter because this body that I just chosen as the new model contains the other body, like they fully intersect. But if that wasn't the case, if there were two bodies that were intersecting or separate or whatever, it would respect them both individually. So somebody asked a question a while ago that was like, how would you keep your, like in this facing operation, how would I keep this face mill from like running into this part? And my answer is partially that I would never actually do this, where I have these parts like super close together. If I were to do something like this, I would just face them all at the same time. But another way to do it would be to, in this setup, select these other bodies as the model also, and that way Fusion knows where they are. It knows that it needs to respect them and not cut into them. So selecting parts that are going to be in your setup as the model makes Fusion recognize that they're there. So hopefully that answers that question. Okay, so that's model overriding, and we're going to see another example of that like in this next part also. So it's a little hard to come up with good, I struggle to come up with good use cases for that. I only like ever think of them when they're actually happening to me, but it is really, can be really powerful. So in this next part, I have this little guy, little gray guy, and he has two holes, and those two holes are covered by surfaces. So those are the holes. And let's say I've already bored them out and they're already cut, and now I just need to finish the surface, this like nice smooth surface. So it's ripe for a parallel, right? Like look at that, only changing in one direction. Parallel is going to work awesome. However, if I just create a parallel operation and I say, you know, so let's find needs to go along the y direction. There's my step over. If I just hit OK, generate a parallel, it's going to, we'll make this a little bigger. It's going to go into those holes, which is my main concern. My main concern is that it just dives right down into those holes, and that's probably not going to be great for my tool. If these need to be nice and sharp, it's going to break that edge pretty badly probably, and you know, just not going to be great. So I don't really like that. So what I can do is use these surface bodies that cover these holes as part of my model. So I'm going to duplicate this operation, and this time I'm going to add those to my model. So I'll check the model box, I'm going to include the setup model, and I'm going to choose these surface bodies as part of my model. So now when I generate this operation, it's going to respect those surfaces as well, and now it's no longer entering the hole. I don't know that I understand your question, Eric. Like, yes, some of these operations were programmed ahead of time, but it doesn't matter. Yeah. Sorry. Okay, so selecting these surfaces basically just kept that parallel out of the holes. There are other ways to do this as well. So I could have done this without having any surfaces. I'm just going to duplicate this one again. This time, I'm going to use something called touch and avoid surfaces. So down here, we have avoid touch surfaces. You choose surfaces of your model off of the geometry. And basically, I can choose the inside faces of these holes. And if I don't check touch surfaces, it's going to avoid those surfaces. If I do check this box, it will only touch those surfaces. So I want to keep it out of these holes, so I'm not going to check this box. I'm going to leave it unchecked. Now I'm avoiding. So when I hit OK, I'm going to generate a toolpath that basically just like avoids the inside of those holes. So this would technically also work. In terms of like it's not diving into the hole. But if I wanted it to be a continuous thing, I would need to use this one where I actually selected those surface bodies and included them as part of the model. I could use some combination of these things. If I make another duplicate of the first one, I could basically say like, I could completely override the model and say only look at these 5 surfaces as part of the model, and then say okay, and now it's only going to do those 5s. That looks basically the same as the one that says avoid. There's a lot of ways to use model overrides and use avoid or touch surfaces to like really pick and choose the specific parts of the model that the toolpath applies to. Now that I think of it, I could even use a machining boundary, right? I could, oops. Under selection, I pick this outer selection, and then these 2 holes, and that should work. So there's a lot of ways. So this is a really good example, actually, of like lots of ways using selections based off the geometry that are machining boundaries, model overrides, or avoid touch surfaces to like really control where your tool goes to. And one side note on machining boundaries, you can also use a sketch. So like if this part I wanted to bound it to like a square around the circle for some reason, I could also just use a sketch contour and select that. I don't have a good example of that ready, but it can be any edge or any contour. Okay, cool. So now we're into our first orange parts, and these orange parts, like I said before, are all just based off of geometry, not a selection. So everything's going to be a little more automatic. It's going to be a little more automated. So this part specifically is for horizontal and pencil. Horizontal is going to go in and find all the flat areas and just machine them, just like machine them flat. So I'll pick a horizontal. If I choose a ball end mill, it'll still work, but horizontal won't know what the step over should automatically be. If I choose a flat or a ball end mill, or excuse me, a flat or a bull nose end mill, it'll use the corner radius and the radius of the end mill to determine like an automatic step over. So I'm going to pick a bull nose because it makes a little more sense to me, because I want that flat bottom part of the end mill to do all the work. And all I have to do is just hit OK. I don't have to make any selections. It's going to automatically go in and find all the flat areas. It knows what the step over needs to be because it knows the tool geometry, and it's done. So it's pretty much just going to go in, do a bunch of offset passes. This is a finishing strategy, so I would recommend not using this for clearing because it is just an offset pass. There's a lot of load on the tool in these sharp corners. So it should just be taking off like a little tiny layer. But that's what that looks like. There are some options in like passes. I can do like more spiral machining. I can set a manual step over. I can, of course, you know, turn down the retraction policy, things like that. But by and large, it's a very automatic toolpath. And then we have pencil, and pencil is going to pretty much just go in and machine internal corners. So along small radii, this is a really good cleaning up strategy for like the very end, and it's going to automatically find all those sharp corners or small corners, so I don't have to go in and pick all of them individually. So I'll choose pencil, make sure I have a ball end mill picked, and just hit OK. So it went in, found all the corners, and is just following along them. If I want this to blend a little more, so if I want it to, you know, maybe there's some leftover from another tool as well, I can go in under passes and just add some more step overs. and maybe make my step over a little smaller. So now it would blend in with this radius and also this flat face down here. So like between the two of these, this would clean up those flat areas and then blend nicely into that radius. Okay, so next on this part, we have this nice like rounded thing, and I'm going to make a parallel. I'm going to use tool number 3. And down here at the bottom of the tool tab, I have something called shaft and holder. And basically, what this is going to do is it's going to use one of these methods to avoid collisions. So rather than just generating the toolpath, you have to go watch a stock simulation, find the collisions yourself, and fix them. Instead, you can enable this shaft and holder collision detection, and it's going to go in and find them preemptively and take some action to avoid them. So a trimmed method is going to just cut off the toolpath before there'd be a collision and restart it at a safe point. Pull away is going to do kind of a little pull away move, so it's going to move away from the part and then re-engage when safe, but it's still one continuous toolpath. And then detect tool length is going to tell you how long of a tool you would need to complete the operation without collision. So that one's kind of, if you have a lot of really long tools or specialty tools or something, that could be useful. But typically, if you have like a fixed tool library and you don't want to go buy a bunch of different tools, you're going to use either pull away or trimmed. So we'll use trimmed. And the thing that it's respecting is you can enable both the use of shaft and holder, or say just one or the other, and it's respecting the clearance amounts that you put in. So like 0.2's on the big side, so maybe I'll say like 0.15 or 0.1 or something, and that's how far away all the geometry needs to stay from the holder the entire time, or it will trim the toolpath. Also in here, I'm going to say 0 degrees is actually correct, and I'm just going to turn this down a little bit because it's pretty big. Okay, and now when I generate this toolpath, so it's trimming away or not applying a toolpath where there would have been a collision, basically. And then I can add another parallel using my longer ball and mill, and just say do rest machining from previous operations. And now this should go in and just clean up where the other one didn't want. Oops. Okay, well, this one did it. Also, turn that up a little bit. When I make a change to a previous operation, by the way, anything that has rest machine from previous operations on it gets flagged as dirty. Oh, I know why. There we go. So that's just going to go in and like fill in the gaps, basically. So now we have a fully machined part. In the next part, so the thing that I originally said about these orange ones is that everything's like kind of automatic. Basically, what that means is that I can really quickly like apply operations from other parts to new parts. So this one over here is like the fits inside this one. So you would think, oh, okay, well, you could probably use the same operations. And so because everything that I've done so far has been based just off of the geometry and not a selection, I can just say copy and paste. So I'm going to hit Control V and just paste them into this setup folder and then say generate. And they're going to like automatically generate functionally into this new part without me having to go back in and select a bunch of, you know, broken geometry selections and things like that. So that's the power of using toolpaths and strategies that look at the geometry rather than looking at selections. Sometimes you can't get around it, and that's okay, but when you can, it's really cool. Okay, so now we're on to this guy, which has fun geometry in that it's got some very steep walls, but a very flat, shallow top. So like we've been seeing, usually operations are good for one of those things, not necessarily both. So what we can do to counteract that is we're going to just kind of take a look at the different strategies and then apply a slope filter to keep them to the parts that they're actually the best at. So we're going to assume that it's already been roughed out, and now what we're looking at for steep walls is 3D contour, which is probably the best one for finishing steep walls, or ramp, which is essentially the same but just takes one continuous toolpath. We'll see the difference a little bit later, but we're going to do a contour for right now. Under geometry, I want to apply a machining boundary of this bottom contour, and I want to make sure under tool containment, I have 3 options. Tool inside boundary is going to keep the tool fully enclosed in the machining boundary. Center on boundary means that the tool can go like one radius outside of the boundary such that the center line of the tool follows along the boundary line, or outside boundary, the tool can go fully outside the boundary, but its outer edge, or like it's the edge of the tool, is always touching the boundary. So I'll say tool outside, and then I can also add an offset here. So whichever direction I've chosen to do to like stay on the inside or the outside, this is an additional offset in that direction. So it's going to go further outside or further inside of the boundary. And then under passes, I want it to go actually 40, I'll say 20. And that's pretty much it. I'm just going to hit OK and see what we get. So from the side, this looks pretty good. And we can see contour is called a waterline toolpath, which basically just means that it has distinct Z heights. So like if water were to rise up, you know, if you have water, it's always the same height around whatever object. So this is like as if the water were raising or lowering by the same amount each time. That's what this toolpath looks like. So from the side, it looks really good. It looks like, oh, this is going to cover it really nicely. But then when we look at it from an angle, we see that it doesn't handle shallow areas very well. So it's kind of similar to how parallel didn't handle those draft faces. So what we could do is duplicate this, and in the duplicate, we can enable machine shallow areas, which is basically the same as machine steep areas in parallel, where it's going to add step downs to those parts where it's really shallow. This looks a lot better. However, there's still pretty large chunks where doesn't look great, and the step over or step down still varies pretty significantly, or it looks like it varies. So maybe, it looks really nice on the steep part, but not so much on the shallow part. So maybe we just want to try containing it to that steep part somehow. So I'm going to make a new contour. I'm going to keep that same machining boundary. And this time, I'm also going to enable, under geometry, I'm going to enable slope. And what this does is it allows me to contain the toolpath to only certain slopes on the part, where the from slope angle is the shallow angle, so it's like the lower limit, where 0 is horizontal, and the 2 is the upper limit, or the steep angle, and that's, the cap is 90 for that, so vertical. So this I want to go on steep portions, so I want it to go all the way up to 90, but I definitely don't want it to go to 0. I want it to go to maybe 60 degrees. So now it's only going to apply this toolpath to parts that are 60 degrees or steeper up to vertical. So now when I hit OK, I need to make sure my tool can go outside the boundary, and now when I hit OK, it's going to just apply that toolpath to the steep portions of the part. So it's staying off of the shallow area, which is great because it didn't really apply very well to the shallow areas to begin with. So now I can choose a better suited toolpath here. So I could say scallop, I could say morph spiral, whatever I want that handles shallow areas well. And this time, I'm going to say go from 0 to 60 degrees, pick my machining boundary, and go. Okay, so this looks pretty good. It obviously went outside my part a little bit, but by and large, this combination, looks pretty good. Whoa. Where it's a lot more uniform than it looked when it was just contour by itself. And I'm using the geometry itself, right? So I could take this same principle where I, these two operations and apply them other places and have them automatically get to something that looks pretty good almost immediately. I would also say I probably wouldn't actually use a morph spiral. That looks a little better. But anyway, last but not least, on this part, it looks very similar to the one from the copied toolpaths, but this time there's a nice sharp corner here. So this is especially for any of you who make a lot of parts with sharp edges like this, or like molds. But basically, there's a setting in one of the operations, or in some of the operations, called contact point boundary. So when I make a new parallel, so I want it to go just to the top height. I want my passes to be along X, and that to be my step over, and I hit OK. So this is just like your basic parallel. What it's doing is it's actually coming up and touching the tip of the tool like right on that edge, which is usually fine, but it's going to break that edge essentially. So it's always going to come up and touch the tip of the tool to the geometry and going to, break that. What we can do instead is, if I duplicate this, all I'm going to do is under geometry, check the box that says contact point boundary. What this does is it makes sure that instead of rolling over the tip of the tool, it's just going to go straight up and make sure that only like the outer edge of the cutting edge touches that sharp corner so it stays sharp the whole time. Did I not check the box? Oops. However, you have to have an actual boundary, which I forgot. There we go. Just to be thorough, I'll show you that the same thing applies. There we go. Okay, so with it off, I'm gonna roll up over the edge. With it on, imagine, if we look at it right from the front, just imagine like this tool radius right here being here. So it's just the cutting edge of the tool is just going to come up and just touch that edge, and then it's going to come back down and keep cutting so that it's not going to roll over and break the edge, basically. So hopefully that makes sense, but that's what contact point boundary is for, and that's how to keep a nice sharp edge on your parts. Okay, so before I get into this little guy, which is just kind of like a smorgasbord part for 3D finishing operations, I want to go over post-processing. So obviously important, you need to get your code to the machine. So to post you can post individual operations, some operations, so I can select by holding Control. I can select different operations that aren't next to each other. I can also hold Shift and select a subset of operations, or I can select the whole setup, which grabs all the operations in that setup, and then right-click and say Post-Process. There are 3 main configuration folders. The first one is generic posts. Everybody has access to these. They are just they come with Fusion, they ship with Fusion, and they're generic, like the name indicates. So this is probably the first place to look. If you have your own post or something, you can also use personal posts. If you're not sure how to find this folder, I would recommend, especially if you're in Windows, just copying this directory, and then you can just paste it into your Windows thing and hit enter, and it'll take you to that location, and then you can save a post in there. And then last we have cloud posts. So this is like, these are the ones that are also saved in that assets project that we just looked at, and I don't have any in there right now, but basically you could upload them via the data panel, or that's probably how I would do it. And then they, just like all the other cloud assets, they're tied to your Fusion account, so they'll always be there. For now, I'm just going to use a generic post. So once I've picked a post, I can, this button, Open Config, is going to open the post configuration file. So it's going to open the file that Fusion uses to post your code. If you want to make post edits or changes or something, that's how you would access that easily from within Fusion. You could also just navigate to this directory and find it that way. If you're on a Mac, that button doesn't exist. And if you're on a Mac, finding this folder isn't quite as easy. There's no directory automatically there. If you need help with that, let me know. I'm obviously not on a Mac right now, so I can't show you, but I do own one to be able to show you with. So next, output folder I can set right now, program name I can set right now, but I can change those when I hit the post button. Last thing is in program comments. This is my last chance to do this. So I I want to make sure this comment is something that actually makes sense. It'll be posted in the code. And then the last thing I want to do is make sure that open NC file in editor is checked. If this is not checked, I personally like to look at my code right away. If it's not checked, I'm just going to save the file but not view it. So that's just me. That's my preference. So when I hit post, and then I can change any properties right here, like use G0. If I change a property, both the property and its value are set to be blue and bold, so you like hopefully see them and that know that it's been changed. And then if I change it back to the default, it's back to normal font. So when I hit post, like I said before, it's going to ask me one more time where I want to save it. If I save it into this local NC directory, just like be aware that that's where it is. That's the default. If I want it somewhere more visible like my desktop, I just need to pick that. So I'll hit save, and it's going to open in our NC editor, which is called Brackets. So this is just like an open source Adobe text editor. If you hate Brackets and never want to use it again, that's okay too. We give you the option under Preferences, General CAM. You can set an external editor. So on Windows, you need to navigate to the exe file. On Mac, you navigate to the application, and you can have it open in like Notepad++ or I don't even know, whatever other text editor you prefer, or if you have like purchased a G-code viewer, backplotter, whatever, you can view it there as well. Lastly, on post-processing, so when you're in that post-process dialog box, you can also access our online post library right away. So this is where all of the like extra posts live that aren't just generic. So we have like, what even is there? Like machine-specific posts, like the Haas ST20, rather than just like the Haas generic, or like for RoboDrill, we have one of those. So you can search, you can sort by vendor, you could pick like complete, now you can use that one. And so you can find basically like any of the posts that we have here that are just more than our generic posts. And then we also have the forum. And this takes you to the HSM forums, but specifically we're going to look at the post-processor forum. And this is where you can go to ask questions, get help from other users, look for solutions. So I usually have a lot of success just searching for whatever problem I'm running into. But you can also, write your own question and things like that. Oops. Okay. So that's post-processing, and we have like under 10 minutes left, 7 minutes. So on this part, basically, I was just going to go through and talk about like individual operations in a little more detail, but we went through parallel already. My one kind of best practice tip trick with parallel is going at 45 degrees can often fix a lot of problems. So like in this parallel, going straight on or going, in one direction, obviously these draft faces get compromised pretty badly. But going at 45, it kind of like, because you're just bisecting the problem area, it sort of becomes not a problem area. So that's one strategy for parallel, is if it feels right, but it's kind of not, you can just go at 45 degrees. Also, on this part, it was basically the same as the part we just looked at, but I wanted to show the difference between contour, which is a waterline, and then a ramp. It makes, like, the biggest indicator to me that ramp is doing kind of like a big spiral down rather than individual steps is with contour. You see these green lead-in, lead-out lines where it's transitioning from one Z depth to a new Z depth. In ramp, there's no green, it's only blue. So that's telling me that it's just taking one big continuous path. So the benefit there is you're not constantly engaging and re-engaging the material. So if your material is really brittle, or if you're seeing like little lead-in, lead-out lines, ramp can help fix those things. Okay. Then we haven't actually seen this one yet, so I'm going to do it from scratch. We have something called spiral, and spiral basically just goes in a circle, in a spiral. The thing to know about spiral is it's best to pick a center point. So I have this sketch that's a center point, and I'm just going to pick it. It will automatically generate one, but usually, in my experience, the generation it varies from good to pretty bad. So it's better to just pick one if possible. Under passes, there's a lot of choices here. Most of them have to do with direction. So like, do you want to go from the inside to the outside? Do you want to go clockwise? Do you want to go, things like that. So a lot of directional options, and then you can also set a spiral mode. So spiral with circles, will add one circle at the very end when it reaches the containment boundary. But the maximum radius has to be smaller than the radius of the containment boundary. So there's kind of some like caveats to that, but basically it adds a circle at the end. Or you can do concentric circles, which is like the contour version of spiral, where it's separate circles that are connected with linking moves. Then you can set an inner and an outer limit. So if I set an inner limit, it's going to start not right at the center point, and then an outer limit obviously limits how far out it can go. And then the step over is a step over, and we'll just hit OK. So that's it, starting 0.1 from the center point and going out to 2.5 inches. So like obviously in real life, I would not do that. Also, I have a bull nose selected. There we go. Okay. Also, radial, which is like the tangential version of spiral. So instead of spiraling outward from a center point, it's going to go back and forth to that center point, radiating from it, if you will. So a lot of similar choices. I can set an inner limit. I can set an outer limit. This time, however, I also get the choice of an angular step because it's radiating at angles. And then I can go from and to specific angles. So if I start at 20 degrees and go to 270 degrees, it's going to only do that portion of the circle instead of going the full 360. And just like in all the other operations so far, 0 degrees is defined by the x direction. So x points along this direction. Actually, that line is basically how x is pointing. So it's going to start 20 degrees counterclockwise from that and go all the way around to 270. So it's starting at 20, going all the way to around 270, taking a 2 degree step over, starting 0.1 inches radially from the center point, going out to 0.75. So I used a lot of the options there that like maybe I wouldn't use in real life. I'd probably have it go all the way around, things like that. But those are the options with radial. And then last, more spiral has kind of a silly name, but it's basically a spiral operation, except you don't need to pick a center point. And it's actually based on the machining boundary. So if I select this as my outer machining boundary and this is my inner, it's going to morph between those two shapes. So it's going to go, that step over is probably way too big. Actually, it's not bad. So it's varying the step over to make sure that it's doing a fluid transition from that circle to the rounded square. So that's what that's all about. It's usually very smooth, really good for organic shapes, but it does require like a machining boundary selection. It can also work with multiple shapes. So I could go from this one circle to these 5 like petal oval shapes, and it can do that transition. It doesn't look quite as pretty as the one boundary selection, but it will do smooth lines between, like a morph between those multiple shapes. That about closes us out right at 3 p.m. But yeah, otherwise, thanks for coming. Feel free to email me any questions. Feel free to download the handout. You will all get a recording of this shortly.